Hello everybody! Our group decided to do an experiment based around water waves. We also based this experiment around the water waves experiment that we did in lab. But for our specific experiment, we were trying to see the effect that sound frequencies would have on the creation of water waves. We wanted to see how water waves would be created in standing water after sound waves from a speaker were introduced. We used 4 different frequencies to see if the changing of the frequencies would cause different wave shapes or wavelengths to occur. We hypothesized that the greater the frequency of sound, the shorter the wavelength measured with the water waves. We also hypothesized that the greater frequencies in sound would result in shorter wavelengths.
Outside of the CLCC basement study rooms, a rectangular plastic tub was placed on a tarp and filled with water to a 3.5 centimeter depth. A ping pong ball was placed at the corner of the tub. A ruler was set on the tub and used as a length scale for video analysis. Using the Sonic by Von Bruno phone app, tones at 60, 70, 80, and 90 Hz were played through a Bluetooth speaker. The speaker was placed against the tub behind the ping pong ball so the sound waves would be directed into the water from that corner. A phone was set on a tripod to take videos of the speaker-produced waves. Flashlights were used for illumination, and an iPad was used to record water depth and frequencies.
The first trial with the sound frequency of 60 Hz was performed, videotaped, and uploaded into video analysis. The points for all the trials were plotted by following a visible wave expanding from the ping pong ball due to the sound waves from the speaker until it couldn't clearly be seen. The position versus time graph further showcases the wave's expanding distance away from the ping pong ball origin. After adding a linear line of best fit, the slope for the position versus time graph was measured, representing the speed of the wave at a frequency of 60 Hz. These same procedures were repeated for the other 3 trials. All of the slopes for the position versus time graphs at different frequencies were relatively close to one another, which is expected since the water tub had a constant depth of 0.035 meters. Shown here are all the calculated and collected data organized in one table. The expected wavelengths were calculated by taking the wave speed and dividing it by the frequency. The expected wavelengths were compared to the actual wavelengths from the experiment, which were calculated by marking the location of multiple crests from a snapshot of the video, finding the X and Y pixels in video analysis, finding the distance between the far points using the Pythagorean theorem, converting to meters using the pixel to meter conversion, and dividing by the number of crests minus 1. The snapshot showcases the actual frequency calculation for the 60 Hz trial. The graph here showcases the relationship between frequency and inverse measured wavelength, including the inverse expected wavelength for comparison. There is a proportional relationship between frequency and inverse measured wavelength, which is relatively close to what is expected according to the inverse expected wavelength line.
Wavelengths and frequencies are inversely related to each other, so that lower frequencies have higher wavelengths and higher frequencies have lower wavelengths. This can be explained in terms of how often the peak of a sound wave reaches the water. So as the length between sound waves decreases, the distance between the peaks of each wave becomes shorter. Therefore, the sound wave peaks produced by the speaker will reach the water more often, correlating to a higher frequency. This can be applied the other way around. As the wavelength increases, a wave peak will reach the water less often, correlating to a lower frequency. The relationship between frequency and wavelength should ideally be observed in this experiment. However, the actual frequencies measured in the experiment only slightly showed a decrease in wavelength as frequency increased, but not enough to make a confident conclusion. This is potentially due to the frequencies being really close to each other in each trial. Nevertheless, there still was a slight decrease observed.
Overall, our data was consistent in that when there was an increase in the frequency of sound, there was a decrease in the wavelength of the water. Some things that could be changed to decrease the amount of experimental errors for future experiments could be placing the light source above the bucket in order to avoid the camera shadow. Another is to have a white tub instead of a transparent tub to make it easier to record on the camera and analyze. A helpful tool that might be necessary is a camera with the ability to record slow motion instead of a phone camera. It is noticeable that our recorded speed was much different than the expected velocity. This is most likely due to the fact that hypothetical situations are not always reflected in real life.